set out. The first half deals with electric fields, starting with point charges, and then moving on to extended charges. And that, guys, is where you have a line of charge or a ring of charge or a rod, etc. And then after that, you deal with conductors, non-conductors, and Gauss's law. All right? You're definitely going to get questions from Gauss's law. When I was doing the course, I hated it. When I started tutoring for the course, I hated it as well. But that's just life. Questions will come from the section. Electric flux, electric fields, and then you move on to magnetism. All right, half of the course is magnetism. Most students find magnetism a little more challenging than electric fields. It takes a little longer to get for most people because of how abstract it is. And generally the advice is that you want to choose one area or one topic in magnetism that you're really good at, sharpen your skills with that one, master it, and then choose one other topic that's just below that one in terms of your competence. All right, and then once you do that and you practice those, then you can move on to others, expand your knowledge, and that generally helps the average student in preparing for exams. All right, so back to electric fields. So question 2. So 2 identical tiny spheres of mass 15 grams are hung from separate silk threads of length 1.2 meters from a common point. Both of the spheres have the same charge, and the angle between the 2 threads is 50 degrees. They ask you to determine Q. So walk me through how you would answer this question. Give me some ideas for how you would approach a question like this.
Well, first of all, well, I am a visual learner, right? So I would have to draw a diagram, something of the sort.
Brilliant. Awesome.
Yes. But I don't know, probably I'm incorrect, but this would seem as a dipole? A dipole, I'm calling it. Oh.
All right. Let me. Any other ideas? So it's not exactly it's not exactly a dipole. It's like a dipole, but it's not exactly a dipole. So a dipole is just 2 charges that are very close to each other.
Oh yeah, sure.
But this is not a dipole because the charges, there's some space between them. There's a distance between them.
Okay.
Right? So I'm going to share my notebook as well. So you should be able to, in a little bit, see both sides of the screen. And we will. I just confirm that you can see both sides of my screen. You can see my entire screen.
Yeah.
Nice. All right. Cool. Let's see how. Yeah. I want to minimize this. All right. So we're going to try and we're going to do a drawing. So Kobe, if you're going to draw this example, how would you draw it? What comes to mind?
I don't know. Honestly.
Hold on. So these look to be a parallel.
It looks like a what?
A parallel, like these. Seeing that they said that they are hung from separate silk threads.
I heard an idea. What was that idea there?
No, I was saying that based on what they're saying, it seems as if they are both parallel to each other.
Nothing? All right. So here's what we're going to do. Okay? They say that you have 2 spheres hung from a common point. Right?
Mm-hmm.
If you're hanging two spheres from a common point, under how do you think they're going to naturally fall? How are they going to orient themselves? Hmm?
You know that, alright, I don't really know how to explain it, but you know the diagram that they keep on repeating over and over with, this, it's hanging from the same point and it goes in two different directions, but it's the same length. And the angle between them would be the 50 degrees. So you would have this triangular looking thing. I don't know if I get what I'm saying, but
I get an idea. So here's the idea that we're working with, right? If you hang something, oh, that's not.
from the same point.
Yeah. If you hang two things from any point, whenever you hang something, how does it orient itself?
Vertical.
When you hang things, yeah, vertical, right? So you're going to have one like this,
Yeah.
and the other one would be something like this, right?
Yes, but the angle would separate them.
So we know that they're separated now because they tell us that the angle between the two threads is 50 degrees. So instead of being vertical, we have a situation where the vertical looks something like this. We have one hanging off to this side. We have one hanging off to this side.
That's what I meant.
Really?
Yeah, something
sure?
like that. Yeah.
All right. Yeah. And then what's this angle right here?
That would be what is it? 50 degrees separate them.
Mm-hmm.
So 25 degrees.
Good. Right, so this would be 25 degrees. Why are they separated? Why are they not falling back in towards the center? What force is keeping them apart?
Because
the electric force.
because the charges on the
Yes.
on the particles are the same.
Are the same. Good. And they point out right here that they're given the same charge Q. So the force, there's an electrostatic force of repulsion that is keeping them apart. Right? Just to let you guys know, this is actually a CXC physics question as well. Although it's set slightly differently for CXC physics, but it usually comes up on the multiple choice section. So you may have seen it before.
Yeah.
All right, cool. So you have your diagram, right? Where do we go next? Because Kobe said she needed a diagram. So Kobe has a diagram. Where do we go from here? Remember, we're trying to find the charge. We're trying to find the charge that is on each of these bodies. We know that the charge on this one, call it A, is going to affect B by repelling B. The charge on B is going to affect A by repelling A. Repulsion means that what kind of phenomenon do we describe when we're talking about repulsion? Repulsion means that there is what actually?
The same charge.
Yeah, but more specifically,
they have the same charge, so they will move away from each other.
Mm-hmm. But what is causing them to move away from each other? Starts with F.
What is causing them to move away from each other?
Yeah. Remember, in physics, things don't just move by themselves. Good. It's a what?
It's a force, but
a force. Good. So there's a force between the two of them. And when it comes to electrostatics and forces, what's the one rule that you're supposed to know? F is equal to?
F is equal. Oh, the Coulomb's law. That's what we're talking about.
Good.
F is equal to K, which is a constant.
Mm-hmm.
Charge on particle 1 times the charge on particle 2 divided by the distance between the two charged particles. But you have to square it, so.
Good. F is equal to KQ on Q2 over R squared. Now, Wills, because Wills pointed out something important about the two charges. What do you know about Q1 and Q2?
The same.
Good. So F is equal to K Q squared over R squared. Right? And R here is the separation between them. So that means that we have to find this distance right here. And we need to find out what, do we need to find out what F is? Can we find F?
F.
Yes.
Once we have we have to find the distance between, oh crap, hold on. What's it equal to? Hold up.
You still with us?
Come in. Wait a try refresh my brain. What you're trying to ask? Oh, can we find F? Or
I remember that at the end of the day, we want to find Q, right?
Oh yeah, because I didn't get
Good. They have not given us Q. What they've told us is that M is equal to 15 grams or 0.015 kilograms. We know the angle. We know that theta is equal to 50, or 2 theta is equal to 50, which means that this angle right here is 25 degrees.
Yeah.
What else do we know? What else do we know?
They gave us the length.
Good. They gave us the
I
length
don't think it's the same.
of the thread. So that means that this distance right here is 1.20 meters.
Yeah.
Yeah. Yes. Good. Nice. So basically, this is all we have. And this is what we're going to use to find Q. So to find Q, we need to find F first of all. All right. Once we find F and we know R, then and we know K is a constant, then it's very easy to find Q. All right.
Yeah. All right.
Good. So how can we find R? We have 1.20 meters here. We know that this angle right here is equal to 25. Good. Can we spy that?
Yeah. No. Yes.
Hold on. Hold on.
I think so. But you died. Couldn't you?
Could you? Maybe.
Or the not necessarily Python, but the angle something.
Or angle something.
There's something with the sine. Oh no, we don't know if it's a sine or a cos of the angle. Never mind. Okay.
Oh, you should know. You're a first year physics student at UMO. You should know.
Yeah, you have the hypotenuse.
Mm-hmm.
So
the hypotenuse is 1.2.
Hypotenuse is 1.20. So if we're using Pythag and using a hypotenuse, then first of all, we're going to take one side of this big triangle right here. We're going to take one side right here. So again, 25, 1.2 x. All right. Now, how I would work this question, because you see, the thing is, my memory is not that good, and I realized this when I was in undergrad. Sorting did not work for me because I would sort x, and I would remember 0.1x. Right? So instead of remembering all of the formulas that deal with trig, for me it just works to stick with the simple ones, the basic ones. So I know this side of the triangle. I can find this side. If this is x, let's call this side y. All right? We can find y because y is going to be equal to what? It's going to be 1.20.
1.20 plus.
Which one do we have?
One. I'm coming.
Right. So let me help you out. So we know this angle right here, right? We know this is 25. What was that, Will?
Yeah.
1.2 what?
What's it asking?
So I was saying we know this angle. This is
Come again.
25.
Yeah.
We know this is the hypotenuse. Compared
Mm-hmm.
to this angle, is this side the adjacent? Is it the opposite or what?
Would we use sine theta equals opposite over adjacent?
Well,
So we have 1.20.
sine is actually opposite over hypotenuse.
Oh yeah, yeah, opposite
Yeah,
over
yeah, yeah.
hypotenuse. Sorry about that.
Right, so we don't even need to find y, so we could do it this way. I was going to find y first and then use it, but you
Okay,
can
let's
say
do that. Oh God. Okay.
But then we have sine, we have theta, and then we have the hypotenuse. So
all right, good. So this means that this side, which is x is going to be equal to 1.20 sine. What angle do we use?
25 degrees.
25. Good. Someone work this out. Tell me what you get here.
$50.7. That's what I got. If we calculate our good.
50.7?
Yeah.
50 points. This is 1.20. You know.
0.507.
0.507.
It's true. I'm sorry.
Question?
So 0.507 meters, right?
Question.
Good. Which means that the total distance from this side, from here to here, is what?
0.507 times 2.
Good.
But question?
Mm-hmm.
Where did we get? They gave us force, and because
No, they haven't given us.
I came in kind of late, so.
All right, so they haven't given us the force. What we're doing question 2, which is this one right here. They've given us the mass of the two spheres. They've given us the length of the two spheres of the strings that are suspending them. They told us that the same charges apply to both of them, and that the angle between this side and this side is 50 degrees. So the approach we're trying to take is that we're trying to find, first of all, the separation between them.
Yes.
We know from Coulomb's law that F is going to be equal to K Q1 Q2 over R squared.
Yes.
We know that Q1 and Q2 are the same. So that gives us F is equal to KQ squared over R squared. So right now we're just trying to find R squared and F, and then we'll solve for Q.
Okay.
Good. So 2 times
Thank you.
0.507 is
1.014.
Did you put that into your calculator, Toby?
Yeah. 1.014.
You actually had to put that in your calculator? All right, cool. 1.014 meters. So we know F. Sorry, we know R. Good. So we need to find F now. How do we find F?
All right.
One of the things that is very important, remember, symmetry, right?
We have one.
Yeah, go ahead.
You can continue talk. I was just going to say that we still need to find the charge.
Mm-hmm.
So.
Well, the charge is the last thing we're going to find. Right?
All right.
Remember, when we find F, F is going to give us Q. So essentially, we know F is equal to KQ squared over R squared. That means Q is equal to F times R squared divided by K. And we're going, what on earth is this? Don't here, do that. Okay. Yeah. Right. Q is going to be equal to the square root of F R squared divided by K, essentially. So what we're going to have to do now is we're going to have to take a look at the forces that each of these spheres is experiencing. And when you get a question like this, one of the most important things to bear in mind is symmetry. Right? Symmetry is very important for E&M questions because in many cases, if you were to look at, in a case like this here, we really only need to look at one of these objects because we know that the charges that they have are the same.
The same.
We know the forces they experience are the same. We know the lengths of the threads are the same. So symmetry is very useful in a question like this. So let's look at sphere A. What are the forces that it experiences? Let me redraw it down here.
So
Just redraw.
it's 10. So would the force be tension forces?
All right, so there's one force that acts upwards like this, that's tension. I don't like the angle here. Let me put it more.
Oh, so that's where the symmetry comes in.
Exactly. So this is T, that's the tension force. Tension, of course, because this is directed diagonally, we know that we're going to have a vertical component. We know we're going to have a horizontal component, although because if you were to let these move, they're not going to move in a straight line towards each other, right? They're going to move to what? Sorry. They're going to move. Describe the path that they move to. If you to let this swing, if you were to immediately remove the charge on this, what's the shape that it would fall through?
What? Vertical? 180?
So it's still attached to the string. It's still attached to the string. It's going to move through an arc, a curved path, right? So, so when we do our, so just bear in mind that that's the path it's going to follow. So this is T X and T Y. So this is T X. What are the other forces that are being experienced?
The field corner.
What are the other forces that are being experienced?
The gravitational force.
Gravity.
Good, good. So gravity. Heaviness. All right. So this is equal to mg. And we know, of course, that this component here is going to be, you're going to have a component right here, mg something something. And you're going to have a component that pulls this way, which is mg something something. Right? Ask the question. Ask the question.
I don't really have a question yet, it's just that probably it's how you do it. I don't know, but it looks fine-ish to me.
It looks fine-ish. All right.
May I learn?
All right. So yes. Let's take it one by one. So you get T, right? You know how we get T, but T is directed upward. Good. All right. And you get mg.
Yeah.
All right. Cool.
Yes, because that's gravitational.
Exactly. Good. What about this angle?
Question?
Can we see? Yes. Yeah.
Could we just ignore the? Do we have to rationalize mg? Because if we rationalize the tension force, there's going to be an upwards tension, and would it just cancel it?
Well, to a point. What you're going to find is that one component. Remember that one component of the weight acts this way, and one component of the weight acts this way.
I can't see what way you're pointing to.
All right, let me do it this way. So one component of the weight. So the weight is going to act downwards like this, right?
Yeah.
Yes.
Remember that the path that this object can take is going to be in the direction of an arc, right? This path is going to be something like this, right? Because if you let go of A is going to swing in a circular path like this, right? So what happens is that if you let go, if you were to rationalize mg, along the path that this takes. One component is going to be directed perpendicular to the tangent right here. So one component is going to be directed like this, right? And one component is going to be directed along the tangent like this.
Okay.
Right? Now the component that is directed perpendicularly, this component right here, is what provides the tension. This is what counteracts the tension.
Oh.
Right here. All right? And the components that, so let me get rid of this because it's actually more accurate to say the component that points along the tangent right here is what would pull A back to the center, right? So it's this component right here that is trying to pull A back to the center. But because A is being repelled by B, it's a force that points in the opposite direction and cancels out this component. So what we're going to do is find this component of the weight and then equate that to the electrostatic force of repulsion. Make sense?
Repeat.
So we're going to find out what the magnitude of this component of the weight is right here.
Yes, that's the force that caused it to move
to the center, but it's not moving to the center because the electrostatic force of repulsion is in equilibrium with it. So if this component is in equilibrium with the electrostatic force, which is pushing this way, then we can say Fe is equal to the component of the weight. Well, however we want to write it.
Okay, thank you.
All right, cool, no problem. All right, so let's just see. Cool, so where were we? So this angle. So back to Kobe, because Kobe said was Kobe that said it looks a little fine? Or was someone else?
It look fine. Somewhere.
Fine. Oh, somewhere. All right, cool.
Yeah.
All right, so let's look back. So remember that
I understand the explanation.
Cool, no problem. So this angle right here is 25 degrees, right? Good.
Yeah.
Remember back to when you first started learning geometry. If you have something looking like this, if this is 25, then this angle right here is what?
Also 25.
Also 25, because
it's like a looking something.
Exactly.
I remember what I'm calling it, but that's what I used to remember it.
So this angle right here is the same as this angle right here.
Yeah.
So what that means is that this angle right here is also 25 degrees. Yes? Because this right here, remember that this is just a close-up of what's happening right here. All right? So what I'm going to do, maybe I should draw a copy. I'm going to see if I can copy it over right here. So this is 25 degrees. Right? I'm just trying to redraw the diagram to make it a little clearer. Hello, this is ugly, but so we said this is mg. This component right here is going to be, so we have one component like this and one component that points towards the center, something like this. Like this. All right? So this is 25 degrees. This is theta. All right? This is also theta. Now, we need to find the component that is bringing this back to the center. That's going to try and pull A back towards the center. All right? So we need to find out if this is mg cos theta or mg sin theta. Which one do you think it is? This is going to be one component, and this is going to be the other component. Which one is cos and which one is sin? Any answer? Anyone know?
To be honest, I'm still trying to understand the whole sign and costing when it comes to analyzing these diagrams, because
Yeah,
sometimes we confuse them. So, yeah.
All right. So that's something you probably will have to do.
Isn't sine away from the angle and then cos is next to it, basically?
Well, in this case, let me just double check. And it gets bigger. This gets bigger. All right. So there is a shortcut method for figuring it out. I really don't like to give shortcuts. Shortcuts can be dangerous. Yeah. So if we draw, let me try and redraw it. Yeah. And guys, it's fine. Remember that it's fine for things to be a blur because you've been, well, I see you've been practicing during the break, but even
Yes, I've been practicing, but
I never want to say that out loud. I never wanted to say it out loud.
no, that's okay. But
Why you drip up so early in the morning?
I've been
Sun just lighting
practicing,
up.
and I
even if
even
you
sent
practice-
Carlos. I sent Carlos so that he could review it, but I understand that you guys are busy trying to get stuff done.
Come on, if you need help, just send us. We'll help you out. Trust me. We after you can only play so much FIFA, right? There's only so much Call of Duty you can play. Boredom will set in. If you need help, just let us. But
That's a lie.
the point is, right.
Objection. Objection.
Even if you've been practicing by yourself, without people to help you, whether it's people in the class or people from your lab group or whatever, it can get challenging. We know.
Okay, but you have to take that back. There's never too much Call of Duty.
We need to give you 5 years and check back in with you and see if you have the same opinion. Anyway, cool. So let's try and figure out the angle here. So this is mg, right? This component right here, we said that this is theta. We have one component that points like this, which means that if you look at this as a right angle triangle here, where this is your right angle, this component right here, this x that we're trying to find, is the same as this side of the triangle right here. All right? Okay. That okay sounds like you're going to have to check it out on your own and practice it. And there's nothing wrong with that, right? So this side right here is this side right here. So if this is theta, this is the adjacent side. So this side is going to be mg cos theta, and this side is going to be mg sin theta. Right? So what we're saying here is that this component right here is mg sin theta. All right?
Okay.
So essentially, we've said all of that to say that the force. Let me see.
Oh, yes.
The force to the right is equal to mg sine theta. And if you're ever stuck in an exam and you can't figure out which one is sine or cosine, think about it this way. As this angle gets bigger, as this angle right here gets bigger, the
But
A is going to want.
But wouldn't the force to the right be wouldn't the force to the right be mg cos theta? Seeing that it's moving horizontally?
No, because remember that you always have to look relative to where the angle is.
Okay. I think I get what you're saying.
Yeah, man. You always have to look at angle. They can throw the angle. Generally it's mg cos if your angle. If this is the scenario you're dealing with right here, if theta is on the horizontal. But right now we have theta on the vertical, which is why it's a little different.
Okay. Oh yes, I just see it.
Yeah, and that's a common way that trick questions get thrown in. So the force to the right is equal to mg sine theta, which is equal to the electrostatic force of repulsion. So basically, what we're looking at here, remember that once we know that this is mg cos theta, but we don't need to consider it any further, because even though this component of the weight is acting downwards, it is balanced by the tension acting upwards.
Yeah.
So we don't really need to consider this. All we need to consider is
Oh.
that A has one component like this. This is mg sine theta acting to the right, and it has Fe, which is equal to k q squared, divided by r squared. This is acting to the left. All right, so this is the force pulling it back to the center, and this is the force that is acting to push it away. And the two of them are in equilibrium, which means that they're equal.
Like, when you call it, take it out as
Find the LCM.
yeah, the LCM.
LCM.
So you'd have A lambda over E
Oh yeah.
plus L.
Tell me your final answer, because we're kind of running out of space.
A
I'm
over
going to assume
lambda.
the final
A
answer is
lambda L
Mhm.
D open bracket C plus L close bracket.
is there a question? If
This is what you got? This is not what you got, right?
No, over.
No.
Oh, okay.
so if at some question, if like somewhere during like the last few parts of the question you don't know
You
how
make a
to
mistake?
no, you don't know how to continue, can you just say
Oh,
if
you
going to,
mean like this? So
like you reach like the third
go
line?
back to what the question says. We see it says K Q over D plus L. You just write it back?
No, like the third line from the end, from what you just wrote. Like, can you just write this will reduce to and you get the full marks?
No.
Please.
Well, you see, the thing is, your lecturer knows they've been teaching for years, and they know that students going to get stuck, and they know that smart students that get stuck are not going to go down without a fight, right? So they're expecting something like that. So let's say D. I'm just going to put the full thing. D plus L. This is going to be D plus L minus, look at that, minus D. Come guys.
That'd be D.
All right, cool.
Bring up that.
And then of course this is going to cancel this. You get K lambda L over D into D plus L. You know that lambda is equal to Q over L. So when you substitute, yeah. So then when you substitute in Q over L, you get
K Q D open bracket C plus L.
Good. All right, so that's the answer. So what you could do, if you get to this point, if you get to this point and you don't remember how to do the LCM, you could, I guess you could look at what lambda is equal to, and then you could substitute what lambda is equal to, and then work your way to get to right here. Yeah, you probably would get most of the marks, if not all. I don't see where someone would be looking to pick off marks, but lecturers are familiar with the fact that students will try to reverse engineer an answer. Right? You have to remember that there are students that will come up with entirely new formulas on the exam as well, and those are probably more of an issue to the lecturer than this. So, nice little question.
Okay, thank you.
Cool. All right, so that's one example of extended charge. Let me see. All right, so I'm looking at I was going to say something about the little birdie. All right. I don't know any little birdies, but there's certain questions I'm looking for a reason. There's a reason I'm looking for these questions. I am going to suggest that we do question number, is it 39 or 36? All right. I'm going to suggest that we do question number 28.
Oh, okay.
Wait, no. I'm looking, it's not 28. 31, sorry.
Mm-hmm.
Cool. Which should also look familiar to you. Yes?
Don't they all look familiar until that day of the exam?
Good point, good point, good point, good point. All right, so we're going to the question 31.
Time is extremely hot.
All right. So this is a Gauss's law question. Okay?
Yeah.
So this is a Gauss's law question. And you know Gauss's law questions when you talk about conducting or non-conducting cylinders or spheres or whatever that are surrounded by a certain geometry. They're surrounded by...
which question are we doing again?
31.
31, not 28?
Yeah. No, 28 looks long and confusing.
All right, so 31.
I mean, you can try 28 for your own practice, but this is challenging. It's not that bad. It's actually not that bad.
No, I said it's not that long because I did it.
Yeah, yes, it's not a bad question. Wait, as in how the question looks or the working out?
You're working.
Oh, you worked it out?
I think so.
Oh, nice. You're about a star student then?
Yeah,
But yeah,
star
it's not.
student.
Nope.
Yeah, so we're not going to do. It's not that bad. Essentially, you have to find the enclosed electric field as a function of the enclosed charge based on the ratio of the inner sphere to the outer sphere. Not a bad question, but for today's purposes, we're going to skip it. So we have 4 minutes left. Let's see how far we can reach in the 4 minutes. How do we start? As usual, we start with a
diagram.
Nice. How are we going to draw this? On an electronic. Let me see. So our sphere.
Did this question?
And then this is going to be Give thanks that you guys don't have to draw on the final exam, because these drawings are hilarious. Every year when I'm marking, let me tell you, we see some drawings every year. Every single year, we see some drawings and we see some answers. It's hilarious.
My Lord.
So you don't have to worry about that this year, assuming that you get multiple choice on the short answer. All right, cool. So they have asked us to determine the electric field for 3 cases. The first case is between A and B. All right. So what does that mean? How are we going to look at that? Essentially, so we have, so this is our cylinder. This is A from the center to the edge. And because this is a cylinder, we have to draw a Gaussian shape that has the same geometry. So we draw an imaginary cylinder that encloses our inner cylinder right here. We're not concerned with anything outside, so we're not concerned with between B and C. We're just concerned with A and everything that A encloses. Now, this shape is a cylinder, right? So it has three surfaces. Surfaces 1, surface 2, and surface 3.
Yeah.
Right? And so what we're going to do is we're going to look at the areas. Let's call this, we're going to take a small segment of the area right here. We're going to call this DA1. It points outwards. We're going to take a small segment of the area here. This is DA2, points outwards, and a small segment of the area here. Well, that should be on the inside right here. And this is DA3, pointing outwards. So you take, basically you're just taking a face of the shape, and the face always points outwards.
Oh,
now,
sorry.
yeah. Now, what's the charge on this? Is it positive or negative?
Positive? Negative?
Positive.
Positive charge. Positive charge.
Q. Good. So that means that the electric field is from Q on the inside is going to be pointing outwards. Right? So that means that what we do is we look at the electric field and try and see how the electric field points to each of these three areas. So right here, well, let's start with this one. So A1, the electric field is going to be pointing outwards like this. All right, so this is E.
We have less than 1 minute, you know.
Yeah, man, this is. All right. The electric field at this point is still going to be outwards. This is E. And the electric field at this point is outwards. So that's E. Right angle. Good. So we have a right angle here and here. So I guess when the stream reloads, then we will. Cool. So let me just take a look. Nice. So when you guys still hearing me, right? Alright. So
Yeah.
after we finish this question, I guess we can probably, I don't know. I'm looking at magnetism, and magnetism is kind of long. Maybe we can find one short magnetism question and then quickly do 1422 because it's almost 12. So let's agree to do it that way. I was going to say I don't know who have party to go prepare for tonight, but then I remembered that we're still in the quarantine. It's all good. It's all good. So we're going to use Gauss's law. Remember, Gauss's law says that the integral, essentially the electric flux to a closed surface is equal to the enclosed charge over epsilon naught. Okay, so this is Gauss's law. So we have to draw that, and this little circle on the integral means that we have to draw an imaginary shape that completely encloses the charge we're looking at and treat each of the surfaces of our closed shape differently.
Yeah.
We have surface 1, 2, and 3, which is what we had before. So what this means is that the integral of E dot dA1 plus integral of E dot dA2 plus integral E dot dA3 is equal to Q enclosed over epsilon naught. All right, which is going to be equal to the integral of E dA1. Here, the angle between these two is what? 90, right?
Yeah.
So this is E dA1 cos 90 plus integral E dA2 The angle between these two is 0. So cos 0.
Oh, yes, yeah. Same
Plus
direction.
integral, yes. E dA3 cos 90.
Yeah, so
And what we see here is that
EDA3
this is going
and EDA1 is going to cancel.
these are going to cancel. All right. So let me just extend this.
But can you do that part again? Like before being cancelled and whatever?
So do the part before everything cancels. That's what you're saying?
Yeah, for that last line you just showed.
All right.
Yeah, just to go over about that part.
All right. So what we're saying is that you look at each of the surfaces, surface 1, surface 2, and surface 3, and you're looking at how the electric field and the area are oriented. So if we draw it, instead of drawing it in 3D, let's draw it something like this. So this area is A, and we've drawn a cylinder around A that encloses it. All right.
Okay.
What we do is we look at, so essentially we treat each surface as if the surface, the face of this imaginary shape we've drawn, is a vector. So this is the first vector, dA1. This is the second vector, dA2. So we basically treat the surface as a vector pointing outwards.
Yeah.
This is going to be dA3. Then the next thing we do is we look at the electric field. But because this is a positive charge, right, we know the electric field is always going to be radially outward. So this is E, this is E, this is E, 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 and so on. And so what we find is that for the third shape, E and dA3 are at right angles to each other. Same thing for right here, right? E is pointing this way, which is at right angles to dA1. It's only when you get to the sides of this imaginary shape, the cylinder, that you find that E and dA are parallel to each other. Right? So because this angle here is 90 and this angle here is 90, and cos of 90 is 0, then this component is going to cancel, and this component is going to cancel as well.
Okay.
Right? And that just leaves us with this component. So what that says is that integral E dot dA cos 0 is equal to Q enclosed over epsilon naught. And so what we can say here is E integral of dA 2 is equal to Q enclosed over epsilon naught. And we can pull E outside of the integral because E is a constant. All right. Now, A2 is going to be the area of this outer face of the cylinder. Do you remember what that is?
What is it?
Right, 2 pi r h.
2 pi r times
H r L, anyone.
Or L, good. So it's going to be E times 2 pi. Did they give us a radius? No, they didn't. R L is equal to Q enclosed over epsilon naught. So E is going to be equal to Q enclosed. Q enclosed, they told us to just Q, capital Q. So we can say capital Q over 2 pi r L epsilon naught. But what do we know here? Remember, we know that K is equal to 1 over 4 pi epsilon naught.
Epsilon naught.
Good. So this is looking like, we don't have 4 down here, we have 2. So basically what we're looking at is a multiple of K times 2. So this is 2K Q over what? Over?
Pi, you no.
So take out the
R
pi.
squared. We're trying to prove E, Where are this?
Over
R
RL.
R.
Good. RL. Good. Good.
Okay.
All right. Is that what they asked us for? Well, yes. 2KQ over LR.
LR. Okay.
Now, if we were to extend the cylinder, they ask us for what happens when R is outside of C.
Outside the C, it includes two charges, basically the same shit, but with two charges.
Good. So if we're looking at R being outside of C, let us.
So it includes minus.
So we'll be looking at a cylinder. So because the shape of the charge is the same, so we still draw a cylindrical shape on the outside of our situation. Scenario. Right. So do I want to erase this?
Lady, listen to me. So.
Who gets in cuss?
No, my lack cuss, but I just remember mother leave. Stop the night. Stop the night, Ross.
What?
So you deal with her, so?
I deal with.
I deal with that way. You know, so I told that you what she said to me, you know, and that's what I want. So anyway, continue.
You know, I tell you about some people, and they look like the nicest people until you. Anyway, so if we're looking exactly, if we're looking at R being greater than or equal to C, that means that we are now outside of this situation. So draw our
outside
Gaussian surface on the outside. All right, like this. But essentially, it's the same situation that we dealt with right here.
Yeah.
Once
it's greater, it's outside.
Exactly.
They have to take into consideration the charge that we just work on
and the negative charge.
Right. So tell me how that's going to work out now.
You're going to how this going on? Also, Carlos explained
If
this.
it says the net charge is like, what does it say the net charge on everything was?
The total charge of -2.
So if the total charge is -2, then on the surface,
that means
the surface,
if it's
all right.
if it's minus, that means it would be going in.
Oh, because if the inner surface is Q, therefore the outer surface has to also B has to also be Q, because it.
Well,
I'm not sure what I'm saying.
It wouldn't be it would be at. Oh, we go. No man. Continue. Come back to me. Because so something about the -2. It would move.
Essentially, each person has a piece of the answer.
So what I was thinking was, if A is Q, the charge at directly B is also Q, and if the net charge on everything is -2, then that's Q. Oh, you have plus Q at A, so therefore there's negative Q at B.
Negative Q at B.
And therefore you have to add like X minus Q plus Q is -2. So X is the charge outside at C is -2, or something like that.
Okay. So,
you would add them?
I'm not sure.
I'll let you work on that one, but I'll explain it this way. So first of all, looking in, we see a negative charge right here, right? This cylinder is negative.
Yeah.
So this is going to be the direction of E.
Yeah,
right
move inward.
E is pointing inwards. Here, E is pointing inwards. And just like before, we know this one going to cancel. Going to cancel. But here now, this angle is no longer 0. This is actually 180 degrees. So this is going to be minus EDA cos theta. Right? well, okay, let me not jump. So plus EDA cos 180 degrees. What that gives you is minus integral of E dA2 is equal to Q enclosed
Enclosed over
over
epsilon.
epsilon
Hold
naught.
up. What just happened now? It kind of blank out. Just
All right. So what we're saying is that
Yeah.
this angle right here is 180 degrees.
Okay.
So we're going to change, instead of having cos of 0, we have cos of 180 down here.
yeah.
Oh,
And then when you take the cos of 180 degrees is equal to minus 1.
Yeah,
oh,
minus
that
1.
was just the only change. Was just moving the
That's the
the
only
0
change.
to 1/8.
Yeah.
Oh, okay.
Yeah, that's the only change. So minus E dot dA is equal to Q enclosed over epsilon naught. All right, and this gives us, just like before, minus E integral dA2 is equal to Q enclosed over epsilon
Over
naught.
epsilon naught.
So minus E times 2 L, what was it, 2 pi LR? Or 2 pi RL? Is equal to Q enclosed over epsilon naught. Now in this case, Q enclosed is going to be the charge on BC plus the charge on A. So this is going to be minus Q plus
Oh yeah, yes.
Q, all divided by epsilon naught. So this is going to tell you that minus E 2 pi RL is equal to minus Q over epsilon naught. But of course, when you cancel the Q, the minuses on both sides, you get back E is equal to 2 KQ over RL. So you get the same answer.
Yeah.
Okay. And then they ask us for the potential.
No, that this isn't bad enough. It just means to understand.
Come on. But isn't that physics in general? Physics is amazing. If you understand it. All right. So quickly, what's the relationship between V and E?
Is it the one where it's a KQ upon R?
E is negative dVdr.
Oh,
E is equal to minus dV dr, which means V is equal to minus integral E dr. So what do they ask us for? They're asking us to find the potential
Difference.
at A minus the potential at B. Right. So essentially what they're saying is they want us to integrate. So first of all, it's the potential between A and B, right? We know that between A and B, the electric field is given by the expression that we just derived, E is equal to 2KQ over LR. Right? So we know E from A to B is equal to 2KQ over LR.
So the limits are A and B.
Right? So we're going to go from B to A and integrate 2KQ over LR with respect to R. Right? Which is going to be 2KQ over L integral dr over R between B and A. All right, tell me what this integral is.
Wait, the negative, there's no negative anymore? It's not a negative integral?
Oh, yeah, there's a negative. Thank you.
Ooh, coffee good.
I'm gonna wake up yet. Yeah,
Nope.
somebody's coffee is good. 2KQ over L. When we integrate dr over R, what do we get? What's our Yes, you get something. All right, remember that if we integral generally, you add 1 to the power and divide by the
Then
new
R.
power. Yeah, but in this case, we can't add 1 to this because this is r to the minus 1 dr. Add 1 to that, we get r to the 0 divided by 0, which makes no sense. So there's a special rule that this is now ln of r and a. Right? So this is going to be minus 2k cubed over L. ln r, we can put ln A minus ln B, or we could write it as minus 2k cubed over L ln A over B. But we can get rid of the minus sign as well by inverting the log. All right. Remember that minus ln A over B is the same thing as ln B over A. So you can write this as 2k cubed over L ln B over A.
So you can always do that to get rid of the minus sign.
Yeah, you can always do that to get rid of the minus sign. And that is actually expected of you at this level. They're not necessarily going to show that on the exam, but in many cases you'll get an integral and you just have to know that rule. A lot of assumptions are made, yeah man. So just bear too much. Cool. So your choice, magnetism or capacitors? And then we move on.
Capacitance.
Both.
Both? Guys, it is 12
I
o'clock
don't
on a
know.
Saturday.
Yeah, and I don't know
Do
nothing.
the time.
No, I'm in a quarantine. I have nothing for do.
Big up yourself. But
I have nothing to do and nowhere to go.
all right. I don't mind helping, but here's what we're going to do.
Lazy.
Right? So if anyone is interested in leaving early, we will do 1422 first and then come back to E&M. All right, so that we can leave early and still get
When is this supposed to be over?
Like an hour ago.
Like, when did we schedule this to be over? Or was there a schedule for it to be over?
Yeah, it was supposed to be an hour and a half, but we started, because we had to switch platforms, we started 30 minutes late.
Yeah, we
so
started late.
12 would have been the time. However, if you guys want to go over, because for every session so far, persons have asked to go over the hour and a half. So if you want to stay, it's cool.
Okay, so I'm just gonna try writing off the ending for this question, then just cut. So
no
So
problem.
Thanks.
we're doing modern physics now, or we're continuing with 14?
We will. Well, it depends. Who's leaving early?
So far, we haven't.
Seems like just me.
Today.
It's just me.
Okay, cool. So we'll do modern, but modern not going to take long. Modern going to take like.
All
Yeah,
right,
because
no
we
problem.
barely do anything.
Exactly.
What is there to talk about?
I continue with my reading, but yeah, we
No,
have
sir,
Gravity.
I went a chapter, 2
Theories.
topics further, and I was like, clearly I cannot go no more because I do not understand what these people
Oh,
are
I
talking about.
understand.
Big up
Because
yourself. I
I'm
never
doing
went
chemistry
further
as
at all.
well, and chemistry kind of helps you.
Big up yourself for doing chemistry.
And biology too.
Wow.
And electronics.
Dramatist.
Wow.
Listen to me, let's stop it.
I will pop your color through the platform, so there you go.
Stop it.
Up your collar, but Corona.
So Justin, there's gonna be a feedback form. So please fill it. Well, everybody, please fill it out. But since you're leaving first, please fill it out as soon as you can.
I don't appreciate how Wills is making food and he cannot send some
This
via
time of
something.
day. Oh my god.
No.
Once this is done, I'm going to go make food.
Kobe,
Yo,
you know that meatloaf in SpongeBob, that virtual meatloaf that Plankton ate?
Lol.
Send some of that.
Wait, question. Am I the only one who, for persons who have the workbook for 1422, am I the only one with like a couple of the pages just kind of mix up?
The pages are always mixed up.
You have the hardcover one.
No,
That's
you're not the only one.
Yeah,
But
the
I
yellow
printed
cover tone.
Yeah.
These books are of the devil.
I printed mine, so I don't have that much of it.
Also on Danielle, sure. I'll if I remember to do the survey thing, then I'll do the survey thing. But where is the survey thing?
Yeah, I'm gonna send it in the chat, in the WhatsApp group as well, and email you. Please fill it
Okay,
out,
then.
guys.
Okay, thank you.
Okay.
I'll do
I
that.
will.
Cool.
Okay.
Cool.
All right.
So,
So we're
well,
doing
thank you, and I
something
guess I'll
now.
leave. So leave. Bye.
Bye,
All right,
Justin.
cool.
Happy Corona Day, and
No,
hope
that
y'all
not
don't
sounds
get
good. No,
Corona.
no. That
Leave
not
with
sound.
that. Leave with that negative attitude. Leave.
No, I said right after, hope y'all don't get Corona.
Hell no.
So I guess I'll just leave then.
Okay.
The happy Corona Day to backwards.
Mhm.
All right, cool. Where is?
I want to go to my laptop. Please to resurrect. I want to go to the.
So this is
Modern
the first
physics.
tutorial.
Get
Yeah,
over
this is the
it.
first tutorial.
Oh, I'm booked, Jesus.
Wait, we're on 1422 now?
Yes.
Yeah, just quickly.
Yeah, it's not a lot.
Alright, give me a second.
Hey, sir.
One.
You know, some other kind of prefer to kind of go over the notes instead of the tutorial, though, because tutorials never really that hard, you know.
Mm.
Okay, to speak for yourself, sir. I would like to go over the tutorials.
Well, due to how I don't have the notes on me,
Yeah,
I'm
it
not
make
a
more
hacker.
sense to do the tutorial questions because then at least the
Exactly.
notes will make more sense or
Mm.
something like that.
Yeah. So what I can tell you though, for 1422, there's plenty of notes and plenty of equations, and many of the equations look like they're describing the same thing. There are
Yes.
about 10 equations that start with E and have
Yes.
R and A and pi and all of them. That it gets confusing. Right?
But is it possible that we could get like not like I'm not gonna say like a formula sheet, but like a sheet.
A cheat sheet.
No, don't say it like that. No, it's like just a sheet that has some of the main formulas that we
The
should
formulas,
know.
trust me.
That sounds like a cheat sheet.
It's not a cheat
Cheat sheet. It's a formula. It's a review sheet.
A
A
review
review
sheet.
sheet.
Right. So here what you do. So let me give you one hint, right? One idea. So each time you're reading the notes and you come across a formula, write it down on a sheet of paper. And just keep doing that.
I do that.
And at the end of the semester,
I've been doing.
I'm talking
no, but you have to
when
wait.
we're in the exam itself, exam pressure.
Oh, you mean no?
And our brains just.
No, I'm talking about no, as in like so on for example like on the boys postulates and hydrogen atoms something like the main formulas that we should know out of that because there's so many different like minor formulas and then the formulas that derive off of other formulas. Like
they're all important.
Yeah,
all of them are important.
Yeah, I think you know
Since we're
physics
doing the
is not for
multiple choice
me.
and short answer instead of like a long paper, normally it goes through like really long derivations, so we need to know all of those.
All right. Do you want me to answer? Do you want me to give you the answer that you want to hear, or do you want me to give you the truthful answer?
The truthful
answer.
You're not going to know what's going to come on the exam until you actually do the exam. And especially with this coronavirus thing, every exam is going to be different from what it was before. Or at least if it isn't, we're just going with the assumption that things will be different, right?
Okay.
Y'all have time to make new questions? Crazy.
No, because we're at the University of the West Indies and academic integrity is important. There's also a possibility that you guys may get different questions because, you know, if they do a question bank with 40 questions and each person does 20, then they will be randomized. So more than likely you will get different questions. And many of the questions
what I've heard in the past is that what usually most of the time what happens, especially in SciTech, what teachers do is that they take say they take 4 tutorial questions and they like change up the numbers. It's literally the same question, the same working out, class questions that are in the book and whatever, same question that are in there. They just put back on the paper because they just don't have time to like redo questions or like come up.
Yeah, but that's very true. But you shouldn't let that lull you into a false sense of security. So Who
It's
in here
not.
does
I just want
electronics?
to like.
Who does electronics? Anyone?
Probably Will.
Repeat.
Will
What
does
did you say?
electronics.
What
Who
happened?
I said it?
I do
Who I said?
electronics.
Cool. So
What
1 year.
happened? What happened?
1 year, Dr. Aiken made a bet, right?
We are doing electronics now. Here.
Dr. Aiken made a bet.
Mhm.
He did a tutorial question and worked it out. Students got it. They got it in tutorial. They got the answer. They mashed it up. All right. They knew exactly what was happening. The man go in the exam and give back the same question, but he turned the circuit by 90 degrees. Problem, right?
What kind of foolishness is that?
Same exact. No, it's a bit.
No, it's a simple thing that the circuit just changed, just turn a different.
Right. That's what I'm saying. You can get this exact same thing, but it will be very difficult for the student that does not understand what is happening. So yes, you do have that. That's a good thing. All right. With FST, chances are you'll get material that you're familiar with. So for 1422, I would say definitely make sure you understand what's happening in the tutorial. And any question, any formula that you see being used on the tutorials is important. So basically, if you've gone through all the tutorials and there's a formula you've never seen yet, you've never used it yet, you probably don't need to use it on finals. Or it's not as important. But make notes of the ones that keep popping up in the tutorial questions, because FST lectures do have a tendency, because we're not testing your ability to SWOT and memorize. We're testing your ability to understand principles and understand procedures and the physics behind it, the science behind it. So if the science behind it focuses on a bunch of equations in particular, those are the ones you want to look at. So, for instance, question 1 here says, find the energy in electron volts of an electron revolving around a hydrogen atom in an orbit of radius 211.68 picometers. All right. Now, how would you do a question like this? How do you approach it?
Right now we'll have so far and try and no, never mind. Foolishness.
Wow. All right. So typically the radius of the orbits, Rn. Remember that in the Bohr atom, electrons orbit at different levels depending on how much energy the electrons have. All right. And so the equation is Rn. The general equation says that Rn is equal to h squared epsilon naught divided by pi m
e squared
times tell you about star students times n squared. Good.
I'm looking at the book.
Turn around. So you notice that everything right here is what? What do you know about all of these terms here?
They have a
they're all constant.
I don't know.
Right? All of them are
yes.
constant. So basically what we're saying is that Rn is directly proportional to n squared. Okay? Or another way of seeing it, Rn is equal to A, this should be A, not alpha, A times n squared. Okay? Now, what's A supposed to be equal to? Did they give you a value for A?
Oh, the acceleration. I don't remember what it is.
All right. A is also referred to as the Bohr radius. And A is basically the value of R at the very lowest energy level. So when n is equal to 1, when n is 1, basically Rn is equal to h squared epsilon naught over pi m e squared. And that is equal to 52.9
PM.
Good.
Oh.
2.9 PM. So basically what we're saying here is that 211.68 is equal to A times n squared. Right?
So basically, you're saying that
or A times, what's A? A we said is 52.9. So let's us, that's N is equal to 52.9 times n squared. So n squared is equal to 211.68. Someone work this out quickly?
4. N is 2.
That means n is equal to 2. So this formula, you know, is important because this allows you to relate the radius of the orbit to the principal quantum number, n, of the orbit. All right? And remember, for chemistry people, n is basically the same as the shell of the atom. Right? Good. So n squared is equal to 2. Now they asked us for energy, so we're looking for a formula that relates E and N.
What the hell?
Don't say that while you're looking through a physics book.
What? No, wait. I'm walking out. So I'm walking around the place.
Okay.
So that's where the energy of 13 point.
Where you're walking around the place?
Yeah.
Wow. Quarantine is not that bad, man. It's not that bad.
My own home. It can't be that bad.
En, as a function of n, what's it equal to? Is equal to minus what? 13?
Minus 13.6 over n squared.
Electron volts.
EV. Good. Another thing you'll notice, one of the reasons why many formulas exist is some of them, well, I don't know how Dr. Penn has organized his notes, but there's some that's specific to electron volts and some that's specific to joules. Dr. Penn is going to work mostly in electron volts. You don't need to work, well, you should know how to convert between them, but you'll get electron volts. This is going to be minus 13.6 divided by 4, which is what?
Negative 3.4 electron volts.
3.4 EV, which is the answer that we wanted to get. So you see immediately, two important formulas you need are this one and this one. But you know this formula is not as complex as it seems because everything here is a constant. Yeah. And this value, if this has a given value, more than likely this will be provided on an exam. So this complex formula is really this simple formula right here. Okay?
Wait, whoa. Where that 13.6 come from?
It's a constant value. Mm-hmm.
Oh.
Mm.
Okay.
All right, cool.
Okay.
All right. So, question 2. You asked you the question 2?
Yes.
We have to stop asking those questions.
You can scroll back.
Sure, no problem. Meeting's gonna end in about a minute and a little bit. So.
Or you can scroll up back. No.
So question 2 says how much work must be done to pull apart the electron and proton if the atom is initially in the ground state, and B, if it's in the state where n is equal to 2. All right. So first of all, if you've pulled apart, if the electron and the proton are separated, then there's no energy of the system. Remember that the energy of the system, En, is equal to minus 13.6 divided by n squared. You have separated the electron and the proton. What do you think the value of n is?
0?
If you have, no,
One.
if you have your proton right here, this is your electron in orbit. The ground state, n is equal to 1.
Oh.
You move it a little bit further out, n is equal to 2. If you've moved it so far, all right, cool. Let me see, who's there? All right, 7 people. Yeah. So what I was saying before is, the further you move the electron from the atom, the further is the bigger the value of n. So if you've moved the electron so far away that it is no longer a part of the atom,
Okay.
what do you think the value of n is going to be?
The 1 then?
No, because 1 is when it's closest to the atom.
Infinity?
Oh.
Say that again?
Infinity?
Repeat what
Yeah,
you
infinity. No, but then shouldn't they have told us how? So they don't tell us how far. Okay, what? If they say that it's being pulled apart, we can assume then that it's infinity unless they don't say it otherwise.
Yep, you can assume that it's infinity. It's been moved away so far. It's been moved infinitely far from the proton, which means that the quantum number is infinity. And if n is equal to infinity, then E at infinity is going to be equal to minus 13.6 over infinity squared, which is 0. Good.
Yeah.
So
That's
good. So what they're saying basically is, you assume if the work done, remember work is equal to delta E. So that's going to be equal to E from the ground state minus E at infinity. But you know that E at infinity is equal to 0.
so then delta E is equal to the E at ground state.
It's equal to the ground state energy. Good. Good. All right. Make sense?
Makes sense.
Yeah.
In a sense.
And dollars.
So basically, is that equivalent to when the initial and then like final?
Yes. Yes. That is it. That is it. That is it. All right. Although technically, just to make sure, it technically should be E final minus E initial.
Yeah.
Should be what?
EI, which would be
E final.
E infinity minus E GF.
Ground.
So we'd get.
So then delta E is
answers
negative ground.
answers. Well, what? Remember that remember that there's already a negative sign. So our answers would end up coming out as positive.
Oh, okay. Yes, hold on. Well,
cool.
Delta E is EF minus. So.
Cool. All right. So in the ground state, we already know EG is equal to E when n is equal to 1. So this would be 13.6 electron volts. If n is equal to 2, then n squared is equal to 4.
Okay.
Delta E would be equal to minus, well, it would be 0 minus 13.6 over 4 AV, which gives us 3.4 EV. Okay.
E equals 0, 0 being ground.
Nice and straightforward.
Infinity.
Mm-hmm.
But 0, the 0, that 0 for part B would be the 0 from the infinity? No.
Yeah,
Oh.
infinity.
Okay.
Yeah. Cool. And then for part 3, they say a hydrogen atom is excited from its ground state to the state with n is equal to 4. Okay. So when you're using the energy absorbed, so here we had EF minus EI. What we're finding here is the energy that must be given to the system. Yes, the energy that must be given to the system. Here we're looking at the energy that we're looking at the energy that must be absorbed by the atom. All right. So this is going to be again EF minus EI. So this is going to be minus 13.6 over that first value of, well, over 4 squared, but minus 13.6 divided by 1 squared. But here's the thing though. Remember that EF is going to be minus 13.6 over NF squared. And EI is going to be minus 13.6 over NI squared. What's common to both of them? 13.6. Right? Actually, it's minus 13.6.
Yeah. Keep on, I forget the minus sign, you know.
Exactly. So what we can do is we can write 13.6. And because the n is in the denominator, this will be 1 over n I minus 1 over n f. Why have we switched the order from f to I?
Because you're moving from initial to final.
The initial will be 1, right?
Initial would be 1.
Because it's the ground state.
Remember, it's minus 13.6 over n f minus 13.6.
Yes, that's why it is.
I. And so, it
doesn't have a thing to do with the order.
Good. So it becomes 13.6 into 1 over n I minus 1 over n.
As to what Carlos was saying, how you would know if it switched, it has to do with whether it is absorbing or if it is emitting.
Or emitting. Good. See, physics is not that hard. Physics makes sense.
Yeah.
Sarcasm though.
Yes, it's okay. You just need practice. You need all the time in the world.
And right now, we have all the time in the world. 13.6, 1 over ni minus, this should be squared. And f is 1 over 16. And this would give you 12.75.
But did you switch it because you said you switched it because it said it was being observed, right? So if you didn't switch it and you would have gotten a negative?
The reason why we switched from I to F is because there's already a negative in this equation. Oh,
because when I worked it out, I had said that I had it as E. What did I do? Had EI minus F, and then I said it was negative.
Yeah, so if you did it backwards, it would still be.
I did it backwards.
I did the entire thing completely backwards.
Yeah, so I got negative 12.5.
Yeah.
All right. So you see, the thing is, if you remember that it's always going to be EF minus EI. Once it's the energy absorbed by the electron,
that's a plus.
EF minus EI.
But when we did it in the tutorial, they gave us delta E equals EI minus EF. Energy.
And then they said that the negative sign indicates that the energy is being absorbed. So it's not necessarily that the answer is negative, it's just saying that it's coming back in.
Yeah.
Yeah.
Oh, that's another way of saying the same. It depends on how you want to look at it. Right?
So
make
we
sure,
putting minus EF, like delta E equals EI minus EF would be wrong at the beginning.
Again, it's kind of tricky to give you an objective answer there because it depends on the perspective that you're coming from. What I was taught to do is to always explain why you write whatever you write if you're choosing, unless a known convention exists. So you see, the thing I was just showing down here where I'd write out what EF is and what EI is, that's what I would do. And if you do that, you'll get the marks. But if you want to stick with the bare minimum that you would start to do in tutorial as well, that's fine. Remember, under exam conditions, you don't have the time to write an entire epistle and to prove the universe. You just need to show them what they're looking for and get your marks. All right?
Okay.
And then question 4 basically is saying that you have the Balmer series. The wavelength of the first line is 656.3 nanometers. They ask you to calculate the wavelength of the second member of the Balmer series. All right. Now, there is a formula. So this formula is a formula for energy. Here, they're asking us not for energy. They're asking us about wavelengths. So when it comes to wavelengths, what's the formula that we use?
1 over lambda is equal to
R1 over NF squared minus 1 over NI squared.
So basically 1 over lambda is equal to R into 1 over NF squared minus 1 over NI squared. Yes?
Yeah.
All right. Cool. Person laughing? That's physics? You're laughing at? Now I have to ask because here's the thing. If you're doing physics and you start laughing to yourself randomly when you're working out physics problems, it's generally a bad sign.
How?
No,
means that just try like a fun.
That's a very bad thing.
No, that's a bad sign.
Anytime I laugh to myself in that exam, I have no clue what I'm doing.
Exactly. Plus, remember, random laughter is a sign of other issues as well. So, just saying. But essentially, I'm not sure if they expect you. The value of R will be given. Actually, more than likely, they will give you what the value of R is equal to. Right? This is something
when we did it,
provided.
When we did it in the tutorial, the last part we had for I don't know why I have wavelength here, but you're supposed to find H for the line H alpha, and I got some like 36 over 5R. I don't know if someone else has that too, but that's the last thing I have for that question.
Oh, well, maybe they were asking you. You have that as well?
Yeah, and then I went down for HB line and then continue.
So maybe. So here's maybe this is what they're having you to do. So
I got
maybe
two
equations,
equations, and then sub them into each
solve.
other. Yeah.
I see. You can do it that way, but they're going to give you the value of R on the final exam.
Good.
Or, if you want, you could just find it directly. Again, this is what I would do. So 1 over 656.3 is equal to R into 1 over 9 minus 1 over 4. You get the value for R. All right, so you'd work out a value for what r is equal to. And then, once you do that, you just use the formula to get 1 over lambda is equal to r into 1 over, what is this now? This is 1 over 16 minus 1 over 4. Or lambda is equal to 1 over r.
Oh yeah, he gave us both ways. Then I have, yeah, 16 over 3r, and then sub in r for 1.097 by 10 to the 7. And I got the answer. Yeah.
Good. And what did you get for your answer?
486 nanometers.
Leah, can you send me a picture of that, please?
Yeah, no problem.
Okay. Thanks.
That's the answer you're supposed to get. So it's nothing too challenging so far. The rest of the course does get a little bit more involved, as you can imagine, but it won't be anything too hard for you. You'll be fine. You shall be fine.
I find this course a lot better than 1421.
Yeah, man, 1421 is generally the harder of the two.
Agree.
I actually preferred it because 1421 made more sense to me. But yeah. All right, so back to 1421. What is this? Oh, this is a 2014 paper.
Leo, you can send me what you have?
Damn, silence.
Oh, yeah. I thought my mic wasn't on mute. Wait, what?
Just send it in the group and call it a day.
All right. Yeah, that makes sense.
What question? We're going back 1421?
Yes.
Are we doing an exam paper or we're doing the tutorial?
That's what I'm looking at. I wouldn't do it. Well, okay. So based on your comfort level, I would say stick to the tutorials first for now, because remember you still have, well, I was gonna say you still have plenty of time until finals, but that's a lie. That's a lie. So you have time though. You have time.
All these coursework come tumbling down.
Yeah, that is true. But you have time. So let's use the tutorials first, and if anything, we can, I guess later on, we can probably discuss. Because we said we're going to discuss another session eventually.
Okay.
So magnetic strength. We've done plenty of proofs, so maybe we shouldn't necessarily do another proof. Let's do question 41. Yes, question 41.
We're on 1421?
Yes, sir.
Yes.
All right.
Yeah, let's do question 41.
Hungry? Yeah, time for eating.
Wow.
Well, offer early.
Sorry about that.
Wow.
I offered earlier.
Wow.
I did offer earlier.
Yeah, but you finished
All
it
this
by
I
now.
use up a lot of nutrients and all these things, man.
So, question. Seeing as how if we weren't in quarantine right now, would you guys be studying this weekend? Or would you
I've been
ended up
studying
in?
from school. From school is out. I've been studying.
That's
I
not the
was
question I
supposed
asked you.
I was
If I,
supposed to be in the grill this weekend for a tournament, and I would have taken my books with me, but to say
For a
work was actually going
tournament,
to be done.
right?
Well, it would be a different question, but I would have my books to me and be reading something. Cannot
Quarantine threw
take
me off
physics.
of my study schedule. That is the issue.
Study schedule.
Actually,
Right.
yeah,
definitely if
Threw
having
me
a
off.
study
that's really
schedule.
I
fun.
bet
In a
half of the
sense,
class would have been in Ochi, and
Yeah,
then half of the class would have been on the road a few weeks
or in the
ago.
yard.
I know them yard.
Exactly.
Well, it would be one of those things out the yard.
Right. Alright, cool. So back to 1421. Let's do. So, two long parallel wires, a distance 2D apart, carry equal currents in opposite directions. So X dot, we have that.
If X is the
And then this is X. Good. If X is measured from the midpoint between those two wires, show that for P located at X less than D to the right, the magnitude of B is given by this and is directed downwards. And if X is greater than D, the magnitude is given by that and is directed upwards. Cool, cool, cool. The person that said they wanted to try this question, because someone else had said this looked like a nice question. What about the question do you like? Is it something specific about it?
Clearly not. I think it was Justine that said that, no?
All right, cool. Well, let us attempt it. So, I'm going to maximize the screen. So the first thing that we have to do, so we have our diagram, and we're looking at the point P. Point P is located right here, this point right here. All right, X is less than D, so X is somewhere between the origin and this point right here. All right. We need to look at the two magnetic fields that are created due to these wires and see what the net field is like at this point right here. So let me extend the screen. And we can start. So do you remember which rule we used to get the magnetic field around a long straight wire?
Right hand rule?
Right hand grip rule, good. So if the current is traveling into the page, what's the direction of the magnetic field?
To the left.
No.
No. Wait.
Out?
What? Oh, upwards.
No.
Wait,
No.
say it again.
Oh my God.
Clockwise.
Grip rule. Clockwise, good. So the right hand grip rule, remember you shape your hand into the shape of a thumbs up. So your hand should form the shape of a thumbs up sign, and then you point your thumb in the direction of the current.
And the current is
into the screen.
So them
So your thumb should be pointing into the screen, and your fingers should be curving
to the
clockwise.
right. Oh yeah.
Clockwise.
Or you just swap the X and the dot.
Oh no.
No,
Clockwise.
don't start it.
So the X looks like this. It's out. Then this is going to go like this. And like that. Cool. What this means is that if you're looking at X, the microphone is Alright, cool. Let's dominate. Dominic, your mic is kind of noisy. Cool. So if we're looking at the first wire A, because the current is into the screen, and because this is going to produce a clockwise field, at this point right here, at point P, the magnetic field B due to A is going to be downwards. Right? Make sense?
Mm-hmm.
All right. Now, because let's look at B. Well, it's not been an issue. Let's call them 1 and 2 instead. All right. 1, 2. So what we can say is that B1 is going to be downwards. B2, now we're on the left of this wire.
Also downwards.
On this side, yes, it's also going to be downwards. So B2 is going to be down here. And so we can say that the net field, yes, B net is going to be equal to B1 plus B2.
So the only problem is going to be the R's.
All right. So what's B from a long straight wire? B is equal to what?
Mu, you know, remember the
mu epsilon.
No, it's not epsilon.
Over 2 pi r.
R, yeah.
Over 2 pi r. Something like that.
Something like that.
I don't remember the formula them either. So.
Wow.
I don't need to. This is not.
True that.
I really don't.
But we can't say that. I don't need to.
When you,
the formula.
I wish I can say that.
When you graduate, but
that is it.
Well, unless you end up teaching.
Because I'm outside the white.
Hello.
Exactly. Wait, what? Teaching is what?
B1, B.
People right and face it. Anyway, so B1 plus B2. Right and face it.
So we can just go so boom from day one and factor them the constants then.
What do you mean?
You can bring up the question sheet, please.
Cool, no problem. Yeah.
Do the man.
Yeah, since the current is the same, like when you sub in that B, the mu is a constant, the current is the same, the 2 pi also a constant. So you factor mu I over 2 pi, and then you're left with, in brackets, 1 over R.
All right.
So 1 over R.
So I wouldn't do it just yet. You could do it that way. The reason I wouldn't do it just yet is because you do get marks for working, and if you make a mistake somewhere along those lines, you may end up in trouble. But we'll factor it out in the next step. Let's do it that way. So for B1, R is going to be D plus X, right? Because there's a distance of D, you have to cover D, and then you have to cover an additional distance X to get to point B. This is going to be 2 pi times D plus X. And then we're going to add to it mu naught I.
Hold on, sir. 1 second. So from the central point, where the perpendicular line, from that central point to point D1, isn't that D?
So this is so you have D.
Yes, then a central point and then a next D.
The next D. But we're at the point right here that is point P, and the distance between here and here is X.
Yeah.
So the distance from the first wire to point P is going to be D plus X.
Oh, what I had in mind was just 2D minus x.
Or you could do it that way. You could do it that way. That may give you some challenges with factoring, but maybe not. Maybe not. Again, as long as you end up with the final answer, then that's fine. I've never worked it that way, but it should give you the same answer. So this is 2 pi into d plus x. This now is going to be d minus x. And then, like we said, we can factor out the mu naught I over 2 pi. We have 1 over d plus x plus 1 over d minus x. I remembered why I didn't want to do this question. I remember why I never wanted to do this question.
Yeah, man, do the maths, man.
Yeah, is it? This is not.
Oh, switch back to the screen so we can see the final answer. Although you're not exactly.
That's cheating, though. That's cheating.
They put it there.
Well, true. It is the difference of 2 squares, though.
Oh.
Okay.
Yeah, I'm gonna get it.
In a way, we get it, because what this would be equal to is mu naught I over 2 pi.
Oh yeah, for true.
Times 1 over d squared. Well, no, but then it's not that easy. Well, yeah, d squared. Yeah, it works out. It works out. I'm not going to skip
distance.
So I'll be lazy. Alright, so d plus x, d minus x
over d minus x plus d plus x. Let's see.
Plus what?
D plus x.
D plus x. Good. So this and this cancels. So we end up with mu naught I times 2d over 2 pi d minus d squared minus x squared, because it's the difference of 2 squares. This cancels this. End up with mu naught I d over pi into d squared minus x squared. Is this correct? Did we make a mistake? No, that's it. That's it.
Oh wow.
Okay.
That's it.
That's it.
Go again. No, as in go back to the answer.
Yeah, that's it.
Right there, so them have x squared minus d squared.
Oh no, for the last one. Where this is
part 2.
Oh, when may I look on the way? Now watch it. Yeah. I got it.
Cool. All right, nice. So let us try part 2.
Wait, the second to last line is mu naught I over 2 pi open bracket dx minus x plus
yeah, where's that?
Plus
what the concept again?
You can.
Honestly, so awful. I'm going to speak, young man.
I'm glad you realized it. So what are you saying, Will?
I don't understand the last line properly. Oh wait.
This one right?
Yeah, the second to last line.
This one right here.
No, the third one. The third to last.
The one where you did the cancellation of the x's. Massimin Castellan he's referring to.
Okay. See, that's what happens when you guys spend so much time together. You get to know how each other thinks. So these.
No. I was somewhere else.
Oh, that's fine. I'm just saying that she already knows where you're concerning. It's a good thing. All right. So you get this one right here, right? This line right here. Move?
Repeat?
So
Sorry,
you
my
get
mother
this
was
line right
talking
here.
to me.
No, that's fine.
Yeah.
So
Yeah.
you get this line right here,
Yeah.
right? Cool.
Yeah, I get
All
that
right.
line.
All right. So what we do is we have to find the LCM. Right?
Yeah.
So in finding the LCM, it's going to be d plus x into d minus x. If we multiply these two together, the LCM of, so we're going to put d minus x plus d plus x. All right? Because this d plus x goes into our LCM d minus x times. D minus x goes into our LCM d plus x times. So that gives us d plus d minus x plus x, all divided by d plus x, d minus x. All right?
Okay.
X minus x and x will cancel, so we end up with 2d. And then this part right here is just the difference of two squares. So we can rewrite that as d squared minus x squared.
Okay.
Cool. All right. I am going to scroll down so we get some space. No, don't annotate. All right. And redraw the diagram.
Well, since part two is just saying that x is going to be now greater than d, so instead of the grip being clockwise, would it be anti-clockwise now?
Which one?
Part two, since it's
so which one of them
the same. It's the same answer except that it's x squared minus d squared instead of d squared minus x squared. So I was trying to see if it's that because the direction of when you did the same right hand grip thing is that the grip is anti-clockwise instead of being clockwise.
Yeah. Which one? So if you're outside here now, then this one is still going to be clockwise.
Oh.
This one, B2 is going to be counterclockwise. B1 is going to be clockwise.
Okay.
So B net is going to be equal to. So B net is going to be equal to. Is it B1 minus B2 or B2 minus B1?
That B1 plus B2.
Well, this is for part one. This is for part one.
So B1 minus B2 then, no? Or B2 minus B1?
Well, think about it. If this is our situation, and we're at a point right here, point P, look at the distances. This is R1. This is R2. Which one is closer?
R2.
Good. So B net is going to be equal to, I would suggest you work with B2 minus B1 because B2 is going to be closer. So B2 is going to be the stronger field. Right? It doesn't really matter because you're not putting in numbers, but that's how I would do it. Okay. So D, and we have less than a minute as well. So what's happening here? 3. This now is X. Cool. So I'm going to tidy up the diagram, and when you guys rejoin, because it's less than a minute, then we just work out the answer. All right?
All right.
He might be speaking to you though. Maybe things will change.
Chemistry.
or maybe it's a trap. You never know. All right, cool. So 59. Uniform magnetic fields through the conducting loop. The magnetic field is into the page.
Yeah.
No, lie. Out of the page.
Oh, the page.
Yeah, the dot. Yes, the dot represents. Oh,
dot.
Lord, very hard to remember this.
Yeah. Nice. Good. So the magnetic field. So we know that R is equal to 3.1 times 10 to the minus 3 ohms. We are told that the magnetic field increases in this way. Actually, this should not be 6.0 t squared minus 7.0 t, or probably some milliwebers and t's in seconds. All right, cool. Did they give us the area? No, they don't.
No.
All right, because usually what they tell us is that that is equal to b dot a or something like that. Yes?
Yeah.
All right. So the fact that they've given this as a standalone, and they're asking us to determine. Wait, what? This question. So look at the question. If you look at this question, first of all, you notice that these answers do not match what they've asked us.
3.4. Different.
Notice they've asked us this. These answers are voltages. Right?
Yeah. Different units.
They've asked us for the induced current.
Right.
So the units are off. All right. I don't know if one of you wants to send an email to Pastor Taylor and point out that while being studious, you discovered something and you might get some extra marks. I don't know.
If it answers emails.
All right, moving on. So we don't know the area, we don't know B, but what we do know is the multiple of both of them. What we're also told as well is that EMF is equal to minus derivative of this by dt, right?
Yeah.
Did they give it to you with the minus sign, or do you?
Let us check back in the book.
If we use the absolute value, then it's just the derivative.
There's no minus then, so
Okay.
it's the second one.
All right, cool. So we know that we have to take the derivative of this. So we're going to differentiate.
Yeah.
6.0 t squared minus 7.0 t.
12
Going to give us
t minus 12 t minus 7.0.
12 t minus 7.0.
Good. So at t is equal to 1 second, the EMF is going to be 12 times 1 minus 7, which is 5 volts. But they've asked us for the induced current, right? To get the current, we know that voltage is equal to, yes.
EMF over R. But then they give a resistance?
They gave us the resistance, yes. So it's going to be 5 volts divided by 0.0031.
I got like 1.61. Or or something to that effect.
Remember that this is milliohms, so this is going to be 1.61 times 10 to
the minus
third power. Come on, third power. And then for the last part, so E when t is equal to 0.5 is equal to 12 times 0.5 minus 7, 6.7 equals minus 1 volt. I is equal to minus 1 volt over 0.001.
3.2.
What's that?
3.2 times 10.
To the third or to the second? Should be a second power.
Oh, it's a second.
Come on, should be a second. So we have the magnitude, but what's the direction of the current?
Not going in.
Well, here's the thing. This is where it gets a little interesting. To get the direction of the current, we have to remember what's called Lenz's law.
Oh,
Right? Which basically means that if okay, it basically means that if a change is occurring in one direction, the system is going to try and counteract it by a change in the opposite direction. So if the external magnetic field is increasing out of the page, the wire is going to try and generate a magnetic field that increases into the page. Right? So what this means is the magnetic field, we know that the magnetic field is out of the page, and we know that it is increasing with time. Right? Magnetic field is increasing with time. So what this means is that the wire is going to try and generate a magnetic field that is going to be into the page. Now, using the right-hand grip rule, if the magnetic field is into the page, what's the direction of the current?
Upwards.
No, right-hand grip rule, remember? Clockwise. So shape you do the thumbs up. Your right hand. Good.
Yeah.
So the direction of the current is going to be clockwise. So this is going to be clockwise for both. That's the answer. All right. Make sense?
Yep.
All right.
Yep.
So let us do one more question.
1 second. So you say that thing clockwise. The current is moving clockwise.
The current is moving clockwise, yes, because the current in the wire is trying to generate a magnetic field that opposes the external magnetic field.
Okay.
Cool.
Is it our last question, or going to be more?
We can actually end here. Because you might need to do some more reading. Yeah, you might need to do some more reading.
Yep, and I also need to go on the road.
You have to do what?
What time is it?
What?
Call the police. Call the police.
It's not time.
Right. The rest of us never heard it. Anyway, so I guess you guys will get in touch and let me know what you're doing.
Daredevil.
Yes, this is quite helpful.
Yeah.
Very.
That's good to hear.
Actually start to make sense now.
Thank you
Thank
guys
you
so
very
much.
much.
Thank you.
Thanks.
A big thanks to Nathan, please, everybody.
Thank
Thanks,
you.
Nathan.
Thank you.
Thanks, Nathan.
And thanks to Danielle for arranging it. Well, Danielle is
Yeah.
out.
Yes,
Thanks,
big up
Danielle.
Daniel.
Guys, next week
Yeah.
I'm going.